Can also be vertical. That means this is the base of the roll is this wall. So even though the F action is tilted, has an angle from the horizontal or the vertical, but the reaction force is always perpendicular to the wall or to the base of this roll. Okay, so this is you need to be how can I say, careful that, because sometimes the base of the roll is not vertical, it's not horizontal, but has an angle. That means the reaction force has to be perpendicular to that angle. Okay. And then the second one is hinge support. And there are two. This time, when the first one, it was just one reaction. Now we have two. Yeah. Hinge support. So angsel or hinge, this is the picture. Excuse me. We'll say a door, knob. Yeah. The actual picture is something like this, or like your door. But in symbol, we make this a triangle and a rod. So this point of contact is this hinge. Yeah. And this reaction is always two. One it's in vertical, R1, and the other is on horizontal, R2. So this one is in Y-axis, this one is in X-axis. Yeah. Even though the action force has an angle or tilted, like this in the picture, but the reaction force always two, one vertical, one horizontal. Usually we put just simply like this. Yeah. Some one going to the top, one going to the right. And if it happened that the result of R1 is negative, that means the actual force is the other way around. It's fine. Even if you make mistake in drawing the picture, it's not a mistake as long as you can define that, oh, the result of R1 is negative something, something Newton. That means the R1 should be in this direction. You can write it down without changing your picture, the free body diagram. Yeah, otherwise if you change, then your calculation is going to be different. So yes, if you have negative result, then just explain that the angle is the other way around. Yeah. Hinge support, 2. Why 2? Because in here, this rod can still rotate, right? So in order for this joint, for this support point not moving, they has to have a reaction in both X and Y direction. While in here, this rod can still move, like here, left or right, in here, top to all bottom, but it will never move to the, in this case, up and down. In this case, in the picture, never move left and right. So that's why the reaction is just perpendicular to the base of the roll. Yeah. And the last one is clamp support. So this one is just clamp really attached to the wall, the rod. So, and this is the action force. So the reaction force now, we have two reaction force plus a moment, as we discussed last week. Yeah, a moment. So we have action force that is tilted like this in the picture, or like this. Now the reaction of this end part of the rod, or here, just one reaction to the y-axis, one reaction to the x-axis, and one moment that react to this F, action F force. Okay, so this. Now let's try to use these three type of support to an example like this. Example 1. Yeah. Determine the reaction force at each support. So we have point A, point B. While between A and B is a rod that has that shape, yeah, with the distance between its point and F is 60-degree angle from the X positive axis, 50 Newton, and located, yeah, between A and B based on the picture. Also, all the information is here. So first step, if we want to know what's the reaction force at A and B, we always need to start with the free body diagram first. We need to take out the picture of this support point, and change it into reaction force. At least the distance. Oh no, no, yeah, the angle or the distance. Yeah. So here, point A, this is a hinge support. Yeah, not a roll. But B is a roll support. So in here, it's a hinge. That means we need to have two reactions. While roll, we need to have just one reaction, which is perpendicular to the base of the rod. So here, two reaction, one reaction. And F, we can also decompose into X and Y direction into this. Yeah. Look, the B point, which was roll, we have this RBY. You can just put RB, but we just need to put Y because we just, yeah, to notice that this is in Y axis. On the A is 2. Yeah. RAX and RAY. Two reaction. And here, 50 sine 60, 50 cos 60 is because of this. Yeah. And as we discussed last week, the composition of the force into X and Y direction. So like this. So if we want to find out what is RAX, what is RAY, what is RBY, based on the first, just use this. If this is on in Indonesia is persamaan keseimbangan or equilibrium, that means this structure doesn't move. This structure doesn't move. That means everything, if you add, has to be equal to 0. So sigma fx equal to 0. Sigma fy equal to 0. And sigma moment in certain place that you want to check is also equal to 0 because none of these are moving. Let's see first the sigma fx equal to 0. What is in the x direction? We have RAX. RAY is not because it's in y direction. RBY is not because in y direction. But 50 cos 60 is in negative x direction. So here, RAX minus 50 cos 60, which means because this one is in a negative x. Is equal to 0. We can calculate this with the calculator, for example, and then we got RAX equal to 25 ton. First question we answer, X. And second question is if you use sigma fx equal to 0, sorry, sigma fy equal to 0. So we check everything that is in y-axis. We have RAY going up, so plus. RBY going up is also plus. 50 sine 60, it's going down, so it's minus. Okay, so we got RIY plus RBY equal to 43.3 ton. Okay, we got this equation. We're not finished because both of these variable, we want to know how much is that. So now we need to find out the sigma moment equal to 0, and we can choose. We can choose in a B, in A, or in a B. And there's no certain rule. It's your job to find out which one that can help me get the answer. Okay. For this, for example, we use point A that as 0. Sigma moment A equal to 0. That means if point A is the center of rotation, if there is a rotation effect, then sigma MA is equal to 0. And why choosing this MA? Because whatever it is that has no length of the force or distance between force and A has zero moment. For example, in point A, RAX has zero moment because it's just going to A. RAY is also has no moment to A because there is no distance. It's going to A. But 50 syntax, 60, 50 cos 60, and RBY has a moment because it has distance to the point A. Okay, so in this case, we can see that if we choose point A as the sigma moment equal to 0, that means we need to find out RBY because this is the only one that we don't know. We know this, we can calculate this, we can also calculate 50 sine 60. This one we don't know, but we don't need to know because there is no moment to point A. Yeah, so what left is RBY. So let's see. If sigma moment A is equal to 0, if this 50 sine 60 going clockwise has the rotation effect of clockwise if this rod can rotate. Yeah. And what's the distance between this force? It's 1. I believe it's 1. Yeah, 1. Yeah, 1 meter to point A. So distance between 50 sine 60 is 1 meter. That's why this is 1. 50 sine 60 multiplied by 1 plus 50 cos 60. This one has also effect, rotation effect to point A in clockwise direction. 50 cos 60 multiply with the distance, which is if you with the transmissibility principle, then move this force here. Okay, and the distance between A and here is 0.5 meter here and here. So here, 0.5. That's the moment because of this force. Now we have RBY. The RBY toward point A has a counterclockwise direction. That's why this one is negative. Okay. RBY multiply with the distance between RBY and A, which is perpendicular with RBY, which is 1 meter plus 0.8 meter. So 1.8 meter here. Okay. And everything is equal to 0. So based on this, we can find out that RBY is now 31 ton. Because we know RBY is 31 ton, we can put it in the previous equation. You can get the RAY as 12.3 ton. Okay, so just normal calculation like we did, but now how we put the R, how many, and the direction of the R is based on these three: clamp support, or hinge support, or roll support. Right. So up to this point, do you have any question? I know this is not in the class that you cannot easily discuss or practice in the board, but please let them know if you have question or something that's still bugging you. Is it all clear? Okay. Yes. Which one? Are you talking about the sigma moment or sigma Fy? Oh yeah, this one there is no plus going where somewhere, right? In front of before the sigma, it should be plus. Is it going clockwise or counterclockwise? Usually we would that, but beside that, I think we can identify that this is plus when it is clockwise. Yes, but what's the question again? Sorry. Yes, for MA. Yes, correct. RAY, we don't need to find RAY and RAX because there is no distance. So even if we put this distance, it's going to be zero. The distance within this force to the A is zero because this force is toward A, right? While this one, and then the BY has distance. So it has a moment. But these two, RAX and RAY, does not have distance, so zero. Okay, that's why we choose A because usually we choose the one that has so many reaction force that we don't know. Here one. A has two reaction force, B has just one. So if you put instead sigma MB equal to zero, it might work, but then you have more calculation to do. This one has only one, two. So I usually prefer to use the sigma moment in the point that has the most reaction. So then you can find the other that has uh, only one reaction and easier to calculate. And after you find this one reaction, you can use it to find the RA1 by just sigma Fx. Sorry, sigma Fy. That's the trick to use. Which point to use the M is the point that has the most reaction force. Yeah. Any other question? Okay. So let's move on then. Now we have what we call a distributed force. Now we have come to from a support point to internal force or this one. Yeah. Based on this distributed line in this case. So force, even if you sit on the chair, the force is not in the center, but distributed in all your body, right? Body weight and all the one that contact the chair on the bottom, all those correction area. This one is to show all this line has this force. Okay. Distributed line work on an object whose length is much greater than their width, or maybe they have some width, but the length is much greater. So we can sort of not considering the width. Yeah, only the length. The width is ignored. And the unit is Newton per meter. And sometimes we use G as gravitation, or could be anything. Okay, but based on a line. While here, the distributed cross section area is distributed based on the cross section. So we have this shape. Sorry. If we this a cross section area, so the distributed force is this circle, and the area of circle is pi multiplied with radius squared. Yeah, here. If we have a rod that is, we take force one part going up and the other part going down. Then in this cross-section area, we have this smaller distributed force in the whole cross-section of this circle, shaped circle. That is, sometimes we say this as a stress. Yeah, but you learn this in material engineering material, I believe. As a stress. Stress means the force divided by the area. Yeah. So this is uh, a force distributed in a cross-section area. Well, if it is volume, then it's the same as density. Yeah. And when you learn about physics or in high school, we have density. Yeah. Basically, it's just force distributed in the volume. Okay. So how can we use this? Let's go to the example. Yeah. Here. We have this rod. It has distributed force along this rod with 30 Newton per meter. So every meter it has 30 Newton force acting downward uh, to the floor or to the earth. And point A is a hinge support. Point B is a roll support with the distance. So for example, for this condition, determine the reaction force that occurs at the support when the system is in equilibrium. It means this rod doesn't move in equilibrium. What's the reaction force in A and B based on this? Yeah. Okay, let's try to discuss this. There you go. We need to do this free body diagram. We can put X in here direction, Y in this direction. And then here in point A, we have is a hinge support. We have RAY and RAX. And point B, we have RBY because it has roll support. How about this force, action force? You have Q, which is the center. Yeah. So all of this, yeah, we focus into this Q. Yeah, into this Q, which location is here, exactly in the middle for this shape. Q is G multiplied with L, or the G, which is 30 Newton per meter, multiplied with the length itself, which is 10 meters. Here. So Q is 300 Newton, but only in this location. So we change from all this distributed force into just one force Q in this exact location, exactly in the middle. From 30 Newton per meter into 300 Newton in Q location. So from this, you just do the normal calculation. Sigma fx equal to 0, sigma fy equal to 0, sigma moment equal to 0, then you can get all the R. Yeah. Let's discuss it. Now, we have sigma fx equal to 0. The only one that has x direction is RAX. There is no other. So that means sigma fx equal to 0, RAX equal to 0, because there is no other force in x direction. So RAX is 0. And this is logical because the acting force is just going downward, all in y direction. That's why there is no x direction of the acting force, and thus RAX is 0. Now, sigma Fy is equal to 0. Now we can find that RAY going up plus RBY going down minus Q that is going up RBY going up minus Q that is going down equal to 0, which means RAY plus RBY equal to 300 Newton. And then to find out these two, we need to use the MA, sigma MA. Again, we use the point that has the most reaction force, which is point A. And based on this, we have Q going down, or it has clockwise direction to point A. Q has a distance, since this is exactly in the middle, the distance to point A is 5 meters. Yeah, Q multiplied with 5. This is clockwise. Minus RBY, because RBY multiply with 10. Multiply with 10, the distance between B and A. And it's minus because it's counterclockwise direction. Yeah. So now we can find that RBY is 150 Newton. So we know RBY, we just put the RBY in this equation and find that AY is 150 Newton as well. Okay. Any question for this? Yeah. How about the other one? Now they have different support system. Okay. Now, here, this is clamping support to point A. Yeah. And the force is distributed only in 4 meter, this 3 meters from A and with 4 meter long. And this distributed force is 10 ton per meters, but in this area. So how can we find the reaction force in A with this clamping support? First, we always need to make a free body diagram and also to change this distributed force into just one force. Yeah, to make it easy to calculate. Since this is a clamping, remember clamping has two reaction plus reaction moment. So in point A, this is the free body diagram. Yeah, if RAX or AY when y direction, we also have MA. And in this case, we just make it in counterclockwise. The logical of this counterclockwise is because of this Q, the distributed force, point A has this distributed force, or in this case Q, has an effect to rotate clockwise. So in order for the A to withstand that rotation effect, it has to have a moment of MA going to the opposite direction, which is counterclockwise. Okay, so this is the reaction force and moment. And Q is, again, you need to find out where is the Q and how much. Yeah, since this is 10 ton per meter and this is in 4, that means Q is in the middle of here, which is 2 meter from here. And how much? Just 10 multiplied with 4, which is 40. Q is 40, okay, in this location. So now we can just calculate sigma fx, sigma fy, sigma ma to find out everything. Yeah. Sigma fx equal to 0. Again, there is no x force, so or x is equal to 0. Fy, what is sigma fy equal to 0? What do we have? We have ray going up and q going down. That's it. Ray minus q equal to 0. That means ray is equal to 40. No, 40 ton because q is 40. And now sigma ma is equal to 0. And what we have here, we have this q multiply with the distance between q and a, which is 5 meters in this case. Q multiplied with 5 minus ma. Since this is clockwise is plus, ma is counterclockwise, we have minus as the reaction moment equal to 0. So now we know Q, so we can calculate ma, and ma is 200 ton meters and counterclockwise. Okay, so here we can find what is Rx, Ray, and ma. Any question up to this point? Any question? Okay. Now, this is a simplistic, I can say simplistic example. We can discuss something more, but I need to give you a new um, link because there's only 2 more minutes because this is not no, the only 40-minute Zoom. So I'm gonna give you the invitation for the other Zoom, and you can join me. I can put it in the chat so we can continue with a more complex example. Okay. Go on. Can you see the chat? And
Yes,
it
Bob.
has a difficulty finding the chat that has new Zoom link. Do you get it?
Yes, Pak. Already, Pak.
Okay, so you can go to that Zoom link. Okay, since mine is gonna
Okay,
finish
Pak.
less than 1 minute, so you can go and enter that Zoom link. Okay, and I'll see you. I'll meet you there soon. All right.
Thank you, Pak.
Right. You join again in this, and we have a bit more time to discuss about the example. So I'm gonna share first the screen. Okay. Now, can you see the one that I'm sharing? Exercise.
Yes, Pak.
All right. So let's discuss. I mean, this one we cannot do it in the board. So I don't know if it is lucky or unlucky, but let's discuss it just at Zoom. Hope you get it. But if you don't, then you can set a time to meet me and discuss about this before the midterm. Yeah. Um, Number one, very easy, similar. It's just that has a 60 angle. So that's why I'm gonna skip it. Okay. Exercise one is similar to the previous, even easier and Indonesian. So it's yeah, just basically just reaction force in A and B. And you can try yourself later on and then check your answer based on this key answer. I know it's Indonesian, but in math, maybe I hope it's fine that you still understand. Yeah, and check like to practice. Yeah, to practice. Now, what I want to discuss is not this simple one, but start from a more interesting one. Exercise number two. Now, this looks better. Yeah, this one is probably a bit more realistic. It's a crane. Yeah, has a mass of 1 ton or 1,000 kilogram and is used to lift a load of 2,400 kilogram. This load. The crane is held at pin A. This is a hinge support, and swing B. This is a roll support. Okay, with the distance, the dimension 1.5 meter, the distance between center of the mass of the crane 2 meter from point A and B, and 1 meter from the mass. Sorry, the load. Yeah, this is 1 meter. Anyway, the picture is making short. This should not be 1 meter. This should be 4 meter. This one meter. So Determine the reaction component at A and B. Just simple. Just what's the reaction force or component? Could be force, could be moment as well. Depend on what type of support. And this is the very general question asking about the reaction and sort of force or component at some point. And I know this is very mechanical, but for us as an industrial engineer, it's also important because point A and B is the critical point. We need to know how big should we, how strong should we maintain point A and B from the structure and weight or anything. So it's going to be still good. The product is still going to be good. If we, for example, we make that crane, we are a company that manufacture crane. That means we need to make sure that point A and B, which is in the critical, we design as such that it's going to be strong enough to withstand the weight, withstand the load. So we need to calculate. And then, sure, this is the first step. But then later on, you're going to collaborate with other people so you know what should be the rod of the crane thickness, you know, length, weight, material, and so on. But starting from here, what's the load? What's the reaction that it has to withstand? This from our part, okay? And that's why we also learn about engineering mechanics because we need to collaborate with mechanical engineering people, with the civil people, with design people, with electrical engineer, and so on. Yeah. So this first is we always need to draw the free body diagram. Yeah. What should we draw? And the point that is the most important point. From here we can see we are being asked point A and B. Yeah, the reaction. So sure, we need to find out what's the free body diagram of A, free body diagram of point B. We also have has the center mass of this structure. So we need to know the G that has the mass. He also has this point, we don't have the point in here, but we know that this is the load, 2,400 kilogram. So there is an action force in here. This is action force of 2,400 kilogram. This has an action force of the mass, yeah, of 1,000 kilogram. And then A and B is the place where the reaction should be. And again, this one use kilogram, okay? So if you want to change to Newton, then you need to calculate with the gravity, right? Weight is mass multiplied with gravity. Like this. There you go. After we calculate with gravity, that 1,000 kilogram we multiply with 9.8 gravity, yeah, say the gravity is 9.81. So we have this 9.81 kilonewton because if 1,000 kilogram become kilonewton, this one also 23.5 kilonewton after we calculate this with gravity. We have point A as a hinge, which has two reactions, AX and AY, or AX and or AY. And B is a roll support, so it's only RB or B. In this case, yeah, this is from a website of Bukafuka, but as you see, this is or AX and AY, and B is just basically or AX and or AY and or B. Okay, so here we go. We have this free body diagram. Without this, you're gonna get confused. Yeah, there you go. So what should we do? Just apply sigma fx equal to 0, sigma fy equal to 0, and sigma moment equal to 0, which you can choose in which point. Yeah. So, for example, we start straight away from the sigma moment. which is totally fine, and point A. Since we have no idea these two, let's just put sigma moment A equal to 0 because then we don't need to calculate these two, AX and AY, or AX and or AY. But we know this, and 9.8, 1 kilonewton and 23.5 kilonewton. We know the distance, 2.8, and also B, we know the distance. So let's just do this to find out what is B. Yeah, sigma M A equal to 0, we have B, since, oh, this one is plus B multiplied with 1.5. So in this case, I think this is plus for a counterclockwise direction. Okay. Sometimes they don't put it, but we can see that, okay, this is counterclockwise effect from B to A, rotation counterclockwise. So, and they put plus, that means it's, for this example of the answer, counterclockwise is plus. So how about this? 9.81 multiplied with 2 meters is minus because it's clockwise. And 23.5 kilonewton multiplied with 6 meter from here to here. 2.8 perpendicular, yeah. Not this side, but here. 6 meter clockwise, which is negative in this case, in this example. You can make different thing, different sign, it's up to you as long as you're consistent. So now we found out that B is 107.1 kilonewton in counterclockwise direction. First question is answered. Now we need to find out AX and AY. Okay, sigma AX equal to 0, sigma FX equal to 0. What is in the X direction? We have only AX or AX and B. That's all. AY, this and this is all, everything is in Y axis. So we don't need to calculate in the X. So because of this, AX plus B equal to 0. It looks like to the right is minus. So it's, yeah, this sounds a bit weird, but it could happen. Yeah. And the X positive direction that we usually have, he put a minus sign. Yeah. And sorry, hang on. Oh, no. This is correct. And X positive is positive. Yeah. Sorry. So AX plus B equal to 0 because we already put the AX is going to the X positive and B going to the X positive as well. So plus AX plus B equal to 0. That means since we know that B is here, yeah, AX is just here, so is exactly the same but with minus. So this is an example that, oh, we previously put AX to the X positive X direction. And now since we get minus 107.1, you just need to add here. AX has a negative value. So assuming assumption, the first option is incorrect and it should go to the negative X direction. That's it. You don't need to change your free body diagram. You just need to put this explanation and it's totally fine. Yeah. So now we know that AX is 107 and going to the negative X direction. Right? AY, just sigma Fx, sigma Fy equal to 0. We have AY, we have 9.8, we have 23.5. So we can calculate now. AY is 33.3 and it's 16 plus. So the first assumption that's going to the top is correct. Okay, and so we can have all the answer AX, AY, and B from this structure. Any question to this point? No question? I hope you get it, yeah.
All good, Pak.
All right. So let's continue for the next exercise. Find out about this. There you go. We have a train. This is a rest on an inclined track. Yeah, it's a train. The weight of the train and the load of what's inside the train is 5,500 pounds. And the picture shows us where is the center of this weight. The train is held by a cable, this cable. And determine the tension in the cable and the reaction at each wheel, assuming that it's in equilibrium. So this train is just rest or hanging on this cable. We have two row support, yeah, and we have a cable in here. The tension means how much tension the cable need to hold, so the train is not falling down. Okay, with all the distance that they provide us in inch and angle as well. Okay, yeah. So how can we make this free body diagram? We need to be careful. The location of this cable is not going to point G. See, this is 24-inch. This is 30-inch. So it's not going to point G. Yeah, first. And this is, you get help by letting you know where is G. Sometimes they don't tell you where is G. Where is this weight? Where is the center of this weight? Yeah, you need to find out yourself. Sometimes that can, but that's for another chapter. We have a chapter that dedicated on finding where is the location of G, but not at this chapter. We have two row on support. So based on this, our free body diagram is looking like this. Look, T, yeah, is the cable. This is the reaction R1 and R2, and G, which is going to the Y, negative Y, but we decompose into this direction, in this direction. And this is already calculated based on this angle. So if we have this as 5,500 going in Y negative, how much is here? How much is, sorry, how much is here? How much is here? We just need to use the trigonometry. Yeah. From 5,500 going down to become 2,320 pound this direction and 4,880 pound going this direction. Okay, decomposition. And why you want to decompose this? Because all the other forces are in this direction. So the y and x axis is not vertical and horizontal, but angle tilted. Yeah. And there you go. You have all the necessary action force and all the reaction that we need to calculate. Yeah. And the distance each other. There you go. Yeah. Between here and here is 6-inch because this one is 24, it's 30. That means between here and here is 6-inch. Okay, this is needed to calculate the sigma moment. Yeah. So we need to find out what is Ri, sorry, R1, R2, and T. Yeah. And here in this case, this is what we know. in point G, we have these two acting force. You can, formula is always the same. Sigma moment equal to 0, sigma fx equal to 0, sigma fy equal to 0. But here we start with the moment. You can start with anything, but if you practice long enough, you might have a hint. Okay, we should start. If it's moment, which point? Okay, depend on which one that you're looking for. Yeah. First, we need to find out R1 and R2. So how can we find out? Let's start with the point A in this case then. Since if we start at point A, we don't need to find R1 since it's going to point A, and we don't need to find T because it's going from point A. Has no distance, it has no moment or anything. So the point A is the point that has the most unknown or the most unknown reaction force. Yeah. While point B only have one. Okay. If you start with point B, you're gonna have a trouble. So it's better to do point A. Sigma moment A is equal to 0. T and R1 we don't need to consider since it's multiplied with the 0 distance. We have this, and R2. So let's just calculate the moment then. 2,320 pounds multiplied with this distance between these to the point A, which is 25 inch. And this one has a clockwise effect. It looks like this key is using minus. So for clockwise, it's minus. This example answer. Okay. Minus 2,320 pounds multiplied with 25 inch. And we have this 4,980 pounds, which has distance 6-inch distance to a point A, which is perpendicular, yeah, to the force. So multiply with 6-inch, and it's minus because it is clockwise direction for the rotation effect, and the clockwise is minus in this case. And R2. R2 has a distance of what, 50, yeah, 25 plus 25 inch from point B or R2, the line of force of R2 with to the A. And this one is what, a counterclockwise direction, and this case is plus, has plus sign. So sigma moment A is equal to 0, and this one, the only thing that we don't know is R2. So then we can calculate what is R2. It's 1,758 pounds. We found R2. Now let's find R1 then. How can we find R1? Then use the moment. Say moment B. Yeah. In point B, we don't know R1. T, we don't know, we don't need to know because it has no distance. R2, we know it already, but we don't need to find R1. And this one, yeah, this and this. So using the same principle of moment B, yeah, 2,320 multiplied by 25, which is the distance between this force to the point B. Counterclockwise, so it's plus, minus 4,980 multiplied with 6, minus because this is clockwise, yeah, and minus R1 multiplied with 50 since it's clockwise, so you can find R1 is 562. No, R2 and R1 is different. You can see that the R2 is the one that need to withstand the most, because this is much heavier than, more than 3 times, or around 3 times of R1. Okay. The T, you just need to put sigma fx equal to 0. If this is the x direction, coordinate, it is y, x. This one, 4,980 minus t equal to 0. So t is 4,980 pounds. toward that direction, to the x negative. So this is now we know all of it, the reaction force. Yeah, based on this problem. Okay. Any question now for this example? Okay.
All good, Pak.
All good, Pak.
If this type of problem is going up in the exam, do you think you can make it? You can do it? Do you think you need more time? Yeah. Oh yeah. Rotation is meaning rotation effect from one point that has force to another point as the base. So it's actually not rotating because this is translating down, but the effect of G in point B, say point B in here in this row, it's like to have a rotation effect. Doesn't mean that it's going to rotate because it's not moving at all. None of this is moving, but the rotation effect of point G of the weight of this train toward this point B and point A, just the effect, as if it's going to rotate, even though it's not. And that's the basic of the moment. If a rotation effect, even though it's not rotating. You can put any places that has rotation effect, but to choose point A or point B as the sigma moment, it's based on your experience or try and error, there. Uh, is it clear or still not clear? Not on the wheel. Oh yeah, because we would now this is also a good question. Why the point A and B is here, not in the wheel itself? Because the question is T. What is T? What is T? This is T. So if we want to know what is T, we need to draw the line of the force acting on the T on the cable. Where's the line? This line. This line. And why not in here? Because the T line is not passing through here. Okay? Not passing through point and in this row and in this row. And also why in point A and B? Because this T line is also getting passed by this R1 and R2. So we need to make a new line as the center of coordinate, x coordinate in this case, that connect all those R and T. So that's why. So maybe if you have this, one of the most crucial things is to find out, so where should I put my coordinate? Is it in here in the roller, or you make something else? But that coordinate need to connect all those reaction force, which T, R1 and R2. T, R1 and R2. So that's why we need to have the new point which connect all those reaction force that being asked to find. And why not in here? Not in the G? Because if we draw a line in the center of the X and Y axis is in G, then it won't connect to the T. Yeah. So that's the reason. And that's the first tricky part of this question. Where is the coordinate? So I can calculate all the sigma M, sigma F correctly. Did I answer your question clearly? Okay. I know this is kind of challenge, and it is a challenge. It's not easy. This is not an easy problem to solve if you don't really understand. Yeah, but this is I just show you so you know in the reality from very simple equation sigma moment equal to 0, sigma F equal to 0. This is what you can get. Yeah. Okay. I hope I can finish in 5 minutes. The last one, if you except if you have another question. Do you have any other question? No? Okay. Another challenge now. It's digital. What's this? It's a control system. Yeah, a pulley system. You can see here the three pulley A, B, and C, and it's is attached to a cable T. This cable is going from the C pulley to the B pulley, and the B pulley connected to another pound weight. Yeah. The question is determine the magnitude of the rope tension T. Only here, this tension rope with this system, and also determine the reaction force on pulley C. Here, this pulley C has a reaction force because it's attached to this beam or rod. Yeah. So this is the question. And how do we do it? Yeah. Always draw the free body diagram. So you won't confuse. What's the free body diagram look like? We have T in here. We have reaction force in here. And since this is a hinge support, we have an X direction and Y direction. We have T in here, that means we have T in here, 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 T as a tension of the rope, and we have the weight. So if we want to make the free body diagram from this system, the answer is, there you go. Here, we have the angle T, and T in here is equal to this T1, so let's say T1, no, T4, yeah, T4. And we have this Fx and Fy or Rx and Ry. That's the reaction. And since this is T4, this one also has T4. And we have two T4 going to the top. And then we have T2, T2. Okay. This is T3, this is T4, this is T2, this is T1. Yeah. I hope it's clear. Yeah. This is T2 and connected to the A pulley to T1, which means T2 is equal to T1, T3 is equal to T4, and T3 is equal to T, the main T. So this is to basically to find out what's the weight going to affect on the T and the Fx and Fy. Yeah. Oh, it's an imagine, but yeah, you can try to understand this, that there are some steps. Yeah, you can start with anything, but say sigma moment O is equal to 0 with T1 and T2. Here O is O. So T1 multiplied with the the distance to the center of the O, the pulley, and T2 also, it means T1 equal to T2. Whenever you have a pulley and you have a rope connected, T1 going up there and T2 going up there too, these two is going to have the same amount. So if you see that since Fy is equal to 0 and looking only at the pulley A, so this going downward 1,000 pounds and going upward T1 and T2, that means T1 and T2, T1 plus T2 is equal to 1,000, which means T1 and T2 both are 500. Since T1 and T2 is 500, T2 is 500. Since this is 500, you can calculate the T3 and T4, which is just what 500 divided by 2. Since it's going 500 downward, we have 2 going upward, which has the same value. So if down is 500, the other 2 that's going up is 250. T3 is 250, that means T is also 250. Now you find that T is 250, this one 250. Yeah. Now we need to find the Fx and Fy in this case. Since we know T 250, now we need to end with the cos 30 or the 30 angle based on sigma Fx equal to 0, sigma Fy equal to 0. You can find what is Fx and what is Fy. Yeah, like this. And then we can find out the Fx and Fy. And what is the resultant? Is you will want to find out what's the resultant reaction of this pulley C. Just you need to use this equation, trigonometric equation, to find out this. Oh, F is 250. Okay. And the direction, then we need to again calculate the direction again of this. But this is a very short explanation of this problem. Yeah. Okay. You can, I know this is another challenge, but you can try to read it again and see if you understand, and we can discuss again the last chance next week. Yeah, through Zoom. Unfortunately, we need to Zoom do again. All classes next week is going to be Zoom, I believe. Yeah, it's very close to the Feed 3. Yeah, another exercise, but we can try to understand. I already put the answer in here, and yeah, Feed we don't have enough time. Okay. So now I'm gonna try to, I think, to stop sharing, I believe, yeah. But I need to share. Very good. What I need to share is the slide. Okay, check the chat